So hello everyone, welcome back to Hasvora Education. Today we'll be revising the chemistry major in P34 practical tips plus the important points. We'll be revising the improvement that you can use to increase the precision in your experiment, because sometimes they ask like a student performed these two experiments and he said that the experiment 2 was more reliable, so you have to justify that type of answer. So we'll also be looking into that together with the limitations that are associated with the enthalpy change questions, and we'll also be looking into the most important tables like the titration table, like the water of crystallization table, like how do we have to make those tables to achieve full marks, because they are easy and you cannot afford to lose marks in these type of easy questions. Also, we'll be looking into the color change that are being associated when we add NaOH and ammonium into the cations, and also we'll be looking into the anions test together with their color change, because a lot of you have the difficulty in identifying the color change. So now let's begin. The first and foremost is the improvements to increase precision in your experiment. So this likely comes as the second question. Like for example, in your paper, it can come as enthalpy change question, which I predict. So in case if enthalpy change question comes in, what can be the limitations in that type of question? First of all, it can be the thermometer. So you can use a more precise thermometer which reads to zero point 0.1 to zero point 0.2 Celsius, because the thermometer that is mostly provided to you in the labs, it just reads to 1 degree and it has a lot of uncertainty in the value. Other than that, you can use a digital thermometer or the thermometer with a smaller graduations or calibration. The other point that can be is that you can use a deeper plastic cup to reduce heat losses, because it will be a bit, you can say it has a bit more distance than the air, so it will not be as exposed than the normal cup. In case if the liquid is volatile, for example, if they are giving you ethanol for combustion to check the check the enthalpy change. In case if it is the liquid is volatile, the enthalpy measured would be affected. Hence, we can cover that fuel, or you can say the liquid, because some of it can actually evaporate and not all of them would be used. So in that case, the enthalpy change would be lesser than it should be. The reaction doesn't go to completion. This is often associated with the magnesium plus the acid enthalpy change questions. Like for example, we are dissolving a magnesium ribbon in an acid, and then we are checking that how much temperature rise uh, does it go to. So in that case, what can happen is that some of the magnesium ribbon can actually be left over, and not all of the magnesium ribbon actually reacts with the acid. So not all solid is dissolved, which will cause the enthalpy change to be lower than it should be. Repeat the experiment with volume of solution required to highest temperature change. So now this point is very important, because sometimes what they do is that they will first of all ask you to carry out the experiment, then they will tell you to make a graph, and then they will also ask you to extrapolate that graph, so you can show them that what volume actually causes the most temperature change. So this can be also an improvement, that you can repeat the experiment with the volume of solution required for the highest temperature change. In case of the combustion question, like as I said in the ethanol ones, not all the fuel is combusted. So this is also a limitation that is associated with it. Use more precise instrument to measure the volume. For example, if we are adding the acid with the measuring cylinder, what we can do is that we can add it using a pipette. For example, if it is 25 cm cube, or you can say a fixed volume, because pipette has uncertainty of 0.06 while measuring cylinder has 0.05. While some of you will now think that 0.05 is lesser than 0.06. But what happens in measuring cylinder is that we take the readings two times. Once at the zero mark and the other one at the volume we read off. So the 0.05 actually multiplies with 2 when we are taking two readings. So it will become 0.1 and the uncertainty actually increases. While in pipette we always take reading once. So this is how you can use a more precise instrument to measure volume. Now the next point is smaller piece of ribbon has greater uncertainty in volume value of time as it dissolves quickly. So this question was particularly asked in a question where the magnesium ribbon and the acid were being reacting. So they asked us that the smaller ribbon or the greater ribbon or the longer ribbon would have a greater uncertainty in the value of time. So we said that the smaller piece of ribbon has greater uncertainty because it dissolves quickly. Now let's move on to measuring uncertainties in titration. This is often a small question like 1 to 2 marks, but some of you are actually confused in how we actually do it. So so you can scale up the apparatus and chemicals to avoid parallax errors. This is in the case if they ask an improvement in your results in the question 1 of titration. So pipette is more accurate as reading is taken once, hence it has an uncertainty of 0.06. To take uncertainty, we divide the absolute uncertainty 0.06 divided by the volume, which is actually your volume. What are you are measuring with the pipette? For example, it can be 25 cm cube or any volume they are telling you to measure. You have to divide by that volume and you have to multiply it by 100. So this will be your percentage uncertainty, and it is actually very low, like sometimes 0.24%, 0.36%, and like that. While in measuring cylinder we measure twice, so hence we multiply 0.05 into 2 and it comes as 0.1. So 0.1 divided by the volume you are measuring with measuring cylinder, it can be 10, it can be 25, it can be 30, or it can also be 50, and then into 100. So this is how you get your uncertainty. Another important formula that they usually ask in the question, that is actually related to the hydrogen peroxide questions, when they actually ask you that calculate the time taken for the insert to become obscure or you can not see it anymore. So in that case we are actually measuring the time, and then at the end they will ask you about the rate of reaction. So most of you do not know how do we measure the rate of reaction using the time only. So rate of reaction is actually equals to 1 over time. So this is the formula, okay? The time is divided by 1. So it will give you the rate of reaction. Now we'll be moving into some of the important tables that you encounter in your papers. The first one, and that is, uh, you can say, mostly comes in the question ones because the question ones are mostly related to titration. So the titration table should look like this. We have to take three readings, but you can also include the rough title, and it is actually more reliable if you take four readings, okay, including the rough title. And we have to first, in the first row we have to include the final bureau reading because it would be greater than the initial one, and then we have to include the initial bureau reading, and we also have to include the unit with it, and then we have to just you can say write volume of fa2 used, or any of the volume, it can be anything, okay, it can be fa3, fa4, it can be it is just a name. Fa2 is just a name given to it. So then you have to include volume of fa2 used or any of the solution that is in the burette, and you have to subtract the final minus the initial. Then you have to uh, show the concordant results. What do I mean by concordant results? Concordant results are that results which have a difference of 0.1 cm cube. So they are called concordant results. Like you can see to 24.30 or 24.40. So they have a difference of 0.1. So we take these two as concordant results, and these will be our best titer. You also have to include this the last row of best titer, so examiner actually knows which values you have taken up. The third, you can see it is 24.8 and it is far away from 0.1, so we do not take it and we just ignore it, okay? And in the case if you do not come up with concordant results, like it can be possible if that your values are a bit far apart, so you can also make up the value so that they are concordant, but always tick and select your best iter which are concordant results with a difference of 0.1, okay, not more than that. Now how do we find the average fa2? Because after this, after making the table, they asked you that find the average volume of fa2 or anything that was in the period used. Then we take the concordant results like the 24.30 plus 24.40, and we divide it by the number of the readings, which is 2, so we end up with 24.35 cm cube. This was the titration table. Let's move on to enthalpy change, which can come up as the second question. So this is particularly related to the magnesium plus the acid reaction. In case if another reaction comes in, um, like I remember in a question, it was about 2 to 3 solutions, and we were actually making up the same volume of 50 cm cube every time, but we were just, you can say, varying the amount of each um, solution added. For example, if we were adding 10 cm cube of fa2, we were adding 440 cm cube of fa3, and then we were just increasing the fa2 to 10 to 50, 10 to 40, and we were decreasing the fa3 to 40 to 10. So this was how we are making. So you also have to include the fa2 and fa3 and the total volume in case if that type of question comes in. This is particularly related to the magnesium plus acid reaction. So the shorter piece of magnesium and the longer piece of magnesium, we will include its mass and the reaction uh, with the shorter piece of magnesium, what is its initial temperature, its final temperature, and its temperature change. So this is a simple one. Let's move on to the water of crystallization by heating. This is particularly used to find the unknown salt in a you can say it can be a carbonate, it can be a nitrate or anything. So first of all you have to measure using the electronic balance the mass of stoppered container plus the lid, and you also have to include the unit gram. So you will be writing the you will be writing the value here. You will be writing the value here. For example, if it comes in like you can say 18.19, and then mass of stoppered container plus lid plus fa2, the salt we are actually you can say heating. So we are going to be heating it, not right now. So if, for example, if it becomes 19.50, so now you can just calculate its difference to have the mass of fa2 used, and it will be before heating, okay, it is just before heating. Then we will just heat it as they give us the instructions, and after that we'll be doing the same, and we will be measuring the change in mass as loss of water in the end. Now let's move on to the most important section, the salts and their color change. First of all, let's jump into anions. In anions, we have the halogens, chloride, bromide, and iodide. So all of them have the same test, like we have to first add HNO3 nitric acid to remove any carbonates or any other chemicals so they may not interfere with our results, and then we add the silver nitrate AgNO3. So the chloride will actually turn white precipitate with the silver nitrate, while the bromide turns a little bit of creamish PPT, while the iodide turns yellow. Cream actually means a little bit of warmer white, okay, not that type of cream, but a little bit of warmer white, you can say warmer white, like it has a tinge of red in it. So then we, in case if they ask us that how are we going to be testing it to, you can say, to just increase or in surety on what type of halogen ion is present in that. So for chloride, what we do is that we add ammonia, aqueous ammonia, and it will actually dissolve in that. The white precipitate actually disappears in the ammonia. While in the bromide, the after adding more than the ammonia that you added in chloride, like a little bit in excess, if you add that in the bromide, it will actually dissolve in that much amount, or you can say a little bit of concentrated ammonia. While the iodide, it never dissolves in any concentration of ammonia. So I have also provided these colors. You can see that the chloride has a little bit of bluish tinge in the white, while the bromide has a little bit of, you can say, warmer, you can say a little bit of um, a red and yellowish tinge in it. So, but not as yellow and as the iodide. The iodide will appear as full yellow color. Let's move on to the carbonate ion. So carbonate ion has a simple test. You just add, you can say, if the solution contains any carbonate, you just add any metal, or you can say any metal salt or carbonate salt, and it will start bubbling and fizzing. Like this, you can say whenever you open an energy drink, how it fizzes. So that is the same type of reaction associated with carbonate. Now let's move on to sulfate and sulfite, SO-204 and SO-203. So both form white precipitate on addition with barium nitrate. And or you can also use the other barium compound. You can also use barium chloride in the case. So both will form barium sulfate and barium sulfide. Both are white precipitate. I have also included the image. So this is how it looks like, like a bit, little bit faint PPT, but you will observe it. It is strong PPT. Okay, so both of them forms the white precipitate. So now how are we going to be confirming that which one is the sulfate, and whether it is sulfate or whether it is sulfide. So if we add a little bit of HCl, the sulfite actually dissolves in on the addition of HCl, while the sulfate, it do not dissolve upon the addition of HCl. Other than that, what you could do is that you could take, um, you can say, you can take a new sample of the sulfate of that solution, and what you could do is that you can add a few drops of KMnO4. The sulfite decolorizes the KMnO4 while the sulfate doesn't. So this can be an additional confirmation to sulfate and sulfide. Now let's move on to nitrate and nitrite. So both release ammonia, or you can say turns litmus paper blue on the addition of aluminium foil plus NaOH, and then we are going to be heating it. And make sure that you just place the litmus paper on the top of the test tube, not inside, okay, because it will react with NaOH and it will be giving the blue color because of that. So just maintain the distance between the test tube, but ensure that it is on the top of it while heating. So both release ammonia and they will turn litmus paper blue on addition of aluminium plus ammonia. Or sorry, not the ammonia, the NaOH. And after that we are going to be heating it. So I've already included the image that how a red litmus paper turns blue. How are we going to be confirming that whether it is a nitrate or nitrite? We can do the same test. We will add a few drops of KMnO4. If it is nitrite, it will turn the KMnO4 colorless, and if it is nitrate, it will not turn it colorless. Now let's move on to the cations. The first of all is the aluminium. So the first column actually contains just the salt solutions. So you can see that whether it is the aluminium, the lead, the zinc, the calcium, All of them has colorless solution. Okay, but it is not a hard and fast rule. For example, if it is actually you can say dissolved with some other salt, or it is a compound of aluminium like aluminium chloride and something like that, it can have a color. Okay, but most of them actually are colorless in their solution form, like the zinc, the calcium, the lead, the aluminium. So they are colorless. When we add NaOH to aluminium, it will show up as white precipitate, like you can see in this one. Let me just mark it. So you can see in this one, it is forming a white precipitate. But when we add a little bit of excess of NaOH, it will dissolve like this. Now some of you are actually confused at what do uh, excess and what do the few drops mean. Excess mean, like for example in this test tube I have taken this much of solution. Now if I add this much amount of ammonia, or it can be NaOH, this is called actually excess, and lower than this it will be a few drops. Okay, so soluble in excess to give colorless solution. Aluminium just dissolves in the excess NaOH to give the colorless solution, while in ammonia it will give a more stronger and you can say dense PPT, and it will be remaining insoluble in the excess. Now let's come to the lead. It also forms a white PPT but more denser, or you can say more sharp PPT than the aluminium, and it is also soluble in excess to give colorless solution. While in ammonia, it also does the same. It will give the white precipitate, and it will um, just remain insoluble. So aluminium and lead are actually the same, as both of them are same. But some of you will be confused that how are we going to be um, figuring out if both of them comes in a same solution. For example, if I add you can say if I add barium chloride to lead, okay, so it will form PbCl. And if I add uh, the same into aluminium, it will form AlCl3. Now AlCl3 is dissolvable in HCl, while PbCl does not dissolve in HCl. It does not dissolve in HCl. So this is an additional confirmation between the aluminium and lead. Now let's move on to zinc. Zinc is just forms you can say a very less PPT when upon the addition of NaOH, and it just rapidly you can say gives the colorless solution upon the addition of excess NaOH. While in ammonia, it also just forms the white PPT and then turns colorless when you add excess of it. On the other hand, calcium, it will give a white precipitate a, a little bit more denser than the aluminium one and less denser than the lead, and it will remain insoluble in excess. While in ammonia, it doesn't give any reaction. There will be no reaction actually. Now let's move on. Now these are the transition metals, ions like the copper, the iron plus 2 and iron plus 3. So copper actually has a solution of mostly of a blue solution when it comes to in the so copper mostly have a blue solution. So copper mostly comes in as blue solution. It is always a blue solution, but sometimes it can be colorless. It is not a hard and fast rule, but most of the times it is actually blue. When you add NaOH, that blue color will actually you can say it will darken a little bit more, and it will remain insoluble in excess of NaOH. You can also differentiate the precipitate from the solution by tilting the test tube a little bit, so the precipitate actually dissolves at the bottom. Then after that we are going to be adding the aqueous NaOH, and so not NaOH, the ammonia. And after that, when we are going to be adding the a few drops of it, the a dense PPT, a light blue PPT will form, and it will be soluble in excess to give a dark blue solution like a sapphire, and it will be actually you will also be able to see through it, that it will not have any of the PPT, or you can say the solid particles. Then comes the iron plus 2. It has a green PPT, like you can say a dirty green PPT, a little bit you can say fainted uh, green, and it will be insoluble in excess. You could see the particles of it in the solution. While the ammonia, it while with ammonia, it also gives the same type of reaction, and it will also be insoluble in excess of ammonia. So one thing to mention here, you can also differentiate it using, or you can say confirm it, when you just tilt the test tube a little bit, which has a iron plus 2, there will be a tinge of brown on the sides of the test tube because it will be rapidly oxidized into iron plus 3. While the iron plus 3, it is a little bit light brownish or yellowish color in color, and when you add NaOH to it, it will form a red brown PPT, and it will be remaining insoluble in excess. While the ammonia, it will also give the same reaction, but there will be a little bit more orange type color with the ammonia. So here I have also included that on standing in air oxygen, the dirty green PPT of uh, iron 2 hydroxide turns reddish brown due to oxidation of Fe2 plus ions. Now I have also included the magnesium, chromium, and manganese, which was not included in these tables. So magnesium actually gives you um, a white PPT, a white dense PPT, and just when you add one drop, it will start giving you the precipitate. It is actually a very dense PPT, and while with the ammonia, it is a little bit of, you can say, a blue tinge. You can clearly see it in the second reaction, ammonia plus MgSO4. It gives a blue tinge type PPT. While the chromium, it is a bit a grayish type. It is a gray green in color, and it will be soluble in with the excess of the NaOH, and it will be remaining insoluble in the excess of ammonia, and it will be giving you a little bit of gray green precipitate in the solution. While the manganese, what happens actually is that whenever you add a drop of it, first of all it will be white, but it will just rapidly turn brown. Okay, like in the second image you can see that this type of tinge of yellow will form. But as I have seen in the real life, so what happens is that when you add a drop of it, it will be white, but it will rapidly turn brown because of the oxidation of manganese ions. So these were the ions, and I have also revised with you the improvements, the tables, and everything. So make sure that you like, share, and subscribe, and share it with anyone you think it will help. I'll be also posting the notes in the description. I'll be meeting you in another video of the expected paper P34 of the May June 2025 session for chemistry. So till then, goodbye.